In this video, we discuss integration formulas and the net change theorem. This is for section 5.4 out of the OpenStax Calculus book, volume 1. This is a relatively short section for us. We won't spend a great deal of time here, and in terms of relative importance, it's not as important for what we'll be doing this semester or even for you next semester. The net change theorem is important for applications, however, it is something that comes up a lot in the real world. Let's take a look at what it says. The net change theorem considers the integral as a rate of change. So we're taking the integral of a rate. When one quantity changes, it says that the new value will be equal to the initial value, what it was before it changed, plus the integral of the rate of change of that quantity. In other words, how much it changed over that time. Let's take a look now in terms of symbols what this means. Again, the new value, which from the definite integral is given as uppercase letter f of b, is equal to the initial value, which is uppercase letter f of a. Remember that a is the initial value, plus the integral of the rate of change. So the integral would be of the rate of change, which of course is the derivative of that function. When you integrate, of course, you must take the antiderivative. Note that the f of b minus f of a is from the fundamental theorem of calculus, part 2, which is giving us this relationship right here. Let's take a look now at an example. This is example 1, which is problem 213 out of your textbook. It says, write an integral that expresses the increase in the perimeter given by uppercase letter P as a function of the side length of the square S of a square when its side length S increases from 2 units to 4 units, and evaluate the integral. Let's first represent the perimeter of a square. In order to do that, we need to write a formula for the perimeter of a square. In a square, all 4 sides are the same length. This that we can write the perimeter as a function of side length, lowercase letter s, as 4 times s. Remember that when you're looking at a square, every side has exactly the same length. And perimeter is simply the distance around the thing. If you were to put a rope all the way around it, how long would the rope be? Now that we have an equation that represents the perimeter as a function, we need to use our formula, which says now I need to take the derivative of that function with respect to the variable. So I find p prime of s, which of course is just 4. To evaluate this now, to find the new value, I need to now find the original perimeter and then add to that the integral. In our case, the integral is changing from 2 units to 4 units. So the integral that we want to have is from 2 to 4, and then I use p prime of s, which is 4 times the differential ds. Since there is no variable in the integrand, then when we integrate it, we end up with 4s, which must be evaluated between the lower limit of integration, 2, and the upper limit of integration, 4. When I compute that, I can pull the 4 out, and that will give me 4 minus 2. That gives me 4 times 2, or 8. In other words, this will give me 8 for the integral right here. Now, to know what the new perimeter is, I need to find the original perimeter. Since it was originally 2 units on each side, then 2 times 4 would tell me that it was originally 8 units long, or 8 units around the entire thing. So in the next step, what I need to do is use the formula. In that case, I know that the original perimeter was 8, and the rate of change now, when I integrated, also gave me 8. And when I add them together, I get 16, which must be the new perimeter, which in fact is the case. If it were 4 on each side, we would have 4 times 4, which would give us the 16. Let's take a look now at the next problem. This is example 2. I've copied the formula again up here so that we have it to refer to. In this problem, which is number 219 out of the textbook, it says, write an integral that quantifies the change in the area of the surface of a cube when its side length doubles from s units to 2s units, and evaluate the integral. The first thing I want to do is draw a cube so that I can understand exactly what's happening. In my original cube, I know that each side had a length of s. So this was my original one, s high, s wide, s long. If I double the sides, then I'm going to get something twice as wide, twice as long, and twice as high. This will give me a different shape for the cube, which will look a bit more like this. Now, when they talk about the area of the surface of a cube, they're talking about surface area. For a cube, you know that when you look at the sides, you have basically 4 sides around the edges, a top and a bottom, or 6 sides total. For a cube, the measure of the area of all 6 sides is exactly the same, since every measure is the same. That means that I can find a formula to represent the surface area. The first thing I want to do is represent the surface area. So I'm going to use SA for surface area. The surface area of my first cube would be 6 sides with a measure of area of s squared. So this would be 6 times s squared. That would give me the area of all 6 sides. Now let's apply the formula. The formula is here at the top. This is the formula that I have for surface area. Now I need to take the derivative of it. The derivative of the formula for surface area with respect to s would be 12 times s. I will take that and put it inside the integral. When I put it inside the integral, I will be differentiating with respect to s, so the differential is ds. The problem that I have here is they didn't tell me exactly how long each side was to begin with. All they told me is it went from s units to 2s units. Then that's what we will have to use for our limits of integration. That means this goes from s to 2s. It can be a little bit confusing to use s in both the limits of integration and inside the definite integral. In a case like that, we would normally go back and remove the s's from inside the definite integral and substitute some different variable instead. Any variable will do as long as it's not the same one that shows up in the limits of integration. Since in a definite integral, any variable used in the differential and the integrand is a dummy variable that will disappear by the end of the evaluation of the definite integral. Now we need to go ahead and compute this value for the definite integral. When I integrate the linear function 12x, I get 12x squared divided by 2. So this leads to the integral from s to 2s, except, oops, my integral is now gone. Instead, I get 12x squared divided by 2, which needs to be evaluated between s and 2s. When I substitute in place of the x the limits of integration, the x will disappear. That's why it doesn't matter what variable I use there. In the next step, I can then reduce the 12 divided by 2 to get 6, and I can do the second part separately. The 6 will be a factor on each one, which means I can factor it out and leave the multiplication for the end. This would give me the quantity 2s from the upper limit of integration minus the quantity s squared from the lower limit of integration. When I evaluate that, at the upper limit, I get 4s squared, and at the lower limit, I get 1s squared. Combined, that gives me 3s squared, which would result in the value of 18s squared. Now, in order to know what the change is going to be or what the new one would be, you would need to compute the original surface area and add that onto it. However, they just asked us for the integral, which we have done, so we have completed the problem. However, to completely use the formula, we would want to know what the original surface area was, in our case, 6s squared, and add that onto the integral to get the surface area of the larger cube here to the right. So the surface area for the larger cube then would be 18s squared plus 6s squared, which would give us 24s squared. Writing that out, we would have the surface area of the larger cube, the new one, would be equal to the surface area of the original cube plus the change, which is the integral that we computed, which was the derivative of surface area with respect to s from s to 2s. Adding these together, we originally had 6s squared plus 18s squared, which tells us that our new cube has a surface area of 24s squared. This means, in comparison to the original, that we have 4 times the area, even though we have only doubled the length of the side. The next kind of problem to be found in section 5.4 deals with the relationship between the position, the velocity, and the acceleration of a particle moving in rectilinear motion. Remember that rectilinear motion means that the particle is moving along a straight line. One of the easiest ways to visualize this is to imagine a car traveling along an interstate. Whether the interstate is traveling east-west or north-south, it is essentially one line in one direction, a unidirectional line. Let's take a look at problem number 224 out of the textbook. It reads, suppose that a particle moves along a straight line with velocity defined by the equation v of t equals t squared minus 3 times t minus 18, where time is between 0 and 6 in meters per second for velocity, but time is in seconds. Find the displacement at time t and the total distance traveled up to t equals 6. You'll remember from an earlier video that we did that displacement is how far you are from where you started when you began your trip. For example, if we are in Denver and we drive from Denver to Colorado Springs, which is 70 miles south, and then turn around and drive 70 miles back north and end up right back in Denver where we started, our displacement is 0 because we ended up where we began. On the other hand, our total distance traveled would be 140 miles because we traveled 70 miles south and 70 miles north to give us a total distance of 140. In order to find these, and starting with velocity, to get from velocity to position, you would need to integrate. Since the relationship is that the derivative of position is velocity, then the integral of velocity is position. Let's write that part down. If I were to take the position function, s of t, and do the derivative, I would come up with the velocity function. That means that if I integrate the velocity function with respect to time, I should be able to get back to the position function at least within a constant. We'll have to know something more about it in order to know what the constant is. Let's now look at our problem. We are told that we're moving along a straight line and the velocity is given by this equation you see in the center. We will need to integrate that equation. We'll put that in as our integrand, which will give us the integral of t squared minus 3t minus 18 in parentheses with the differential dt outside. We're also told that time goes from 0 to 6 seconds. Those would be our limits of integration. The lower limit is the smaller value 0, and the upper limit is the larger value 6. To find displacement, we simply integrate the velocity function as it is. It will take into account automatically the north-south travel and give us the net displacement, the net change. In order to get total distance, I will need to take the absolute value of this function, which is a little bit different, so we'll save that for just a moment. The easiest part is, of course, displacement. Let's find the displacement now. To get displacement, what I want to do is integrate. I can split this into 3 separate definite integrals, or by now you may be able to keep it together but still perform them as if they were separate. Again, you can factor any constant to the front of the integral, provided that it's common to all the terms in that integral. I'm going to split it into 3 integrals, though you can do the integration directly from the original form. This would give me, as a result, t cubed divided by 3 by using the power rule for integration, minus 3t squared divided by 2, and minus 18t. All of this needs to be evaluated between 0 and 6. In the next step, we need to plug in our limits of integration to get the values. This would give me, plugging in the 6 first, 6 cubed over 3 minus 3 halves times 6 squared minus 18 times 6. Now plugging in the lower limit of integration, I will need to combine those and then subtract the result from the first part. This would give me 0 cubed over 3 minus 3 halves times 0 squared minus 18 times 0. We love to have 0 for a limit of integration because, of course, as you notice, this entire second part just goes to 0. That leaves us with just the evaluation of the first part. 6 cubed is 216 over 3. 36 is the value of 6 squared divided by 2 would be 18. 18 times 3 would give me, yes, I'm calculating it out. This would be minus 54, and then 18 times 6 would give me 108. If I combine the negative 54 and the 108, I end up with 162. This gives me 216 thirds minus 162. If I combine these together, I should end up with 90, I believe. Let's compute that again just to be sure I haven't messed it up. 216 divided by 3 minus 162 gives me negative 90. Okay. 216 divided by 3 results in 72, so it would end up with a negative 90. What does that mean? Oops, I've put the answer back here. This means I have negative 90. Negative 90 what? Well, I integrated velocity, so this must be position, so this must be miles. What does that mean? Well, in the sense of the Denver versus Colorado Springs, if I started in Denver, the negative 90 means I must now be 90 miles south of Denver. It's negative because I traveled in the negative direction, which on a north-south line would be south. This is my net displacement. This is where I ended up. It is not, however, the total distance. How could I find total distance? Instead of finding the displacement as we did here, now we want to find the total distance. To find total distance, you must strip off the north-south part of your equation. Stripping that off means stripping off the sign, which means taking the absolute value of the integrand before you integrate. If you do it afterwards, it won't tell you anything except that I am 90 miles from Denver, but won't indicate north or south. It does not, however, give me the total distance. To get total distance, the absolute value must be done on the integrand before you integrate. In that case, that means that we need to consider our velocity function and look at its absolute value, which will almost certainly mean a piecewise defined function. Let's recall what the velocity function is. You'll see here that I have produced a graph of our velocity function, but instead of using the variable t, I've had to use x. T is used in Desmos for a different purpose, which is to create a parameterized equation. So in this case, what I want to look at is basically this graph here, and I want to figure out how I can look at it. Since our function only extends between 0 and 6, I can restrict the graph by putting in braces with the restriction. A brace is one of the curved parentheses. Put in 0 less than or equal to, x is serving as our t, less than or equal to 6, and then close your brace. This will give you only the portion of the graph that's between 0 and 6. You can see the graph here. Notice that there is some indication that direction must be changed. Since this is the velocity, however, notice that the velocity function is always below the axis, meaning that the velocity is always negative. This must mean we're traveling in that direction. Now, if I were going to take the absolute value of this function, what would change? What I can do now is I can copy this and I can paste it into the equation below by copying it with Control C. I can enter the absolute value symbols and then I can paste in my picture. I can also then close up that symbol like that, and then I can copy the same restriction that I had up here, which is that x goes between 0 and 6. Control C will copy, Control V will paste. If I do that, look at what has happened now to my graph. It has flipped the entire graph up to the top portion. You'll notice that in this particular problem, 100% of the velocity graph was below the axis. And when I take the absolute value, 100% will now be above. This will enable me to compute the difference. Now let's take a look back at what we had originally on our equation. I was looking now to find the total distance. Because I know from the graph that in fact the total distance was in fact all headed in the same direction, since the velocity was always negative, it was always headed south, I can simply take the absolute value of this and that will give me the correct distance, which would be 90. This would not be the case if part of the graph were above and part of the graph were below. Then I would have to split the integral into different pieces. The parts that were above the graph can be integrated without the absolute values. The parts that are below the graph cannot. To complete this problem, before we move on to a different example, we need to find the displacement at time t. To find the displacement at time t, we need to integrate the function from 0 to an unknown t. Since t appears as a limit of integration, then we will need to use a different dummy variable inside the expression of the integrand. Recall that our integrand is given by t squared minus 3t minus 18. To use a dummy variable, I will again use x. This would give me x squared minus 3x minus 18 with respect to x. I know I'm starting at 0. That was given in the original description of the problem. but now I want to go to some unknown time value that's between 0 and 6. To do that, then, what I need to do is integrate. I will do the integration and then plug in the limits of integration. This will again give me x cubed over 3 minus 3x squared over 2 minus 18x, evaluated now between 0 and t. This will give me the displacement function, which when I plug in the t will be t cubed divided by 3, or 1/3 t cubed, minus 3t squared divided by 2, or minus 3/2 t squared, minus 18t. Now, what will we have for the next part? Since the lower limit of integration was 0, and since every term has at least a single factor of x, then plugging in the lower limit of integration will result in 0. That means that this is, in fact, my displacement function at time t. Now let's take a look at a slightly different example where part of the velocity function is above and part below the t-axis. This means that for part of the trip you are traveling north and part of the trip you are traveling south. In this case, you'll see that we must split the interval into different pieces. Here is example 3. Suppose a particle moves along a line again, we'll assume a north-south line, with a velocity given by t squared minus 5t plus 4, again over the time interval from 0 to 6 hours. We want to find the displacement function again and the total distance traveled. And for fun, we'll go ahead and find the net displacement from 0 to 6 hours as well. This time, let's start with the displacement function. To find the displacement function, I need to integrate from 0 to t. This is going to give me the following: the integral from 0 to t of t squared minus 5t plus 4. This is displacement again, so this means that it does not need to take into account the absolute value. We only do absolute value when we're looking for total distance, not net distance, which is displacement. In this case, I'm not going to split it separately. I'm simply going to do it in my head. The antiderivative of t squared is t cubed divided by 3. The antiderivative of negative 5t would be negative 5t squared divided by 2. The antiderivative of 4 is 4t. Now I need to plug in the limits of integration, but since the lower limit of integration is 0, that part will drop out. This simply gives me t cubed over 3 minus 5/2 t squared plus 4t as the displacement function over the time interval from 0 to 6 hours. What is that net displacement? I could either plug it into that equation or I can reintegrate from 0 to 6. So my net displacement in the 6 hours is given by both formulas. This would be the integral from 0 to 6 of t squared minus 5t plus 4 dt, but that's also what I would get if I were to plug the 6 into this formula, since this formula gives me the displacement at an arbitrary time t starting at 0 hours. That would give me 6 cubed divided by 3 minus 5/2 times 6 squared plus 4 times 6. This is 216 divided by 3 minus 5/2 times 36 plus 24. Working out the arithmetic, 216 divided by 3 would give me 72, and half of 36 is 18, and 18 times 5 would give me 90, plus 24. This results in basically 94 minus 90, which gives me a net displacement of 4 miles. Because it's positive, this means I ended up 4 miles north of where I started. This is not, however, the total distance I've traveled. Let's take a look at the graph on Desmos to see what has happened. You'll see that I have again produced a graph of the picture only over the interval from 0 to 6. Notice that this time our velocity function starts with a positive velocity since it's above the axis, meaning that it's traveling in the northerly direction. Then it stops and turns around. The velocity is 0 here at 1 and again at 4, meaning that the particle's not moving. Then the particle is traveling in the southern direction because the velocity is negative. When I get over here between 4 and 6, velocity is positive again, indicating that the particle is moving to the north again. Now I'm going to produce the graph of the absolute value. When I look at this is representing net displacement, but with the velocity graphed instead of position. If I now want to look at total distance traveled, I must consider the absolute value of that graph. In this case, you'll notice that the part that was below the axis has been flipped up. You'll also notice this forms sharp corners and cusps here at these points, which means we cannot integrate across it. But that's okay because we want to integrate in pieces anyway. The parts that were originally above don't need the absolute value. Only the part that was between 1 and 4 needs the absolute value. Let's look at how to apply this back to the function. To apply the formula now, I need to integrate to get total distance. I need to integrate where the function is all represented with positives. That means since it's already positive between 0 and 1, I can simply put in here the regular velocity function, which is minus 5x, or t, whichever you prefer, if you want to use t instead, plus 4 with respect to time. I can do the same thing for the last part between 4 and 6 because it's positive there as well. However, what about the part in the middle? The part in the middle is where it dips below the axis. Remember that when you define the absolute value of something, it simply gives you that thing, provided that thing is not negative, and gives you the opposite if it is negative. In other words, what we need to do to find this centerpiece where it was below the line between 1 and 4 is to take the opposite of every term in the integrand. That would give us negative t squared minus plus 5t, the minus becomes a plus, and minus 4 dt. This, when we compute it, will give us the total distance traveled. We know the antiderivative for the first and the last integral since it's the same one we've been doing all along. It will be similar for the center integral, except that the signs will be opposite in nature. Let's represent it now. This will give us t cubed over 3 minus 5 halves t squared plus 4t evaluated between 0 and 1. In the center then, I'm going to have a minus t cubed over 3 plus 5 halves t and minus 4t, this part integrated from 1 to 4. The last integral will be the same again as what it was originally. T cubed over 3 minus 5 halves t squared plus 4t evaluated between 4 and 6. Take a moment to pause the video and do the calculations, then turn the video on to check your answer. While the arithmetic and the algebra can be a bit challenging, I hope that you did finally come up with a value for the total distance traveled of 15. That is what you would get if you did the absolute value of the integrand before you integrated. Again, in order to do that, you have to split it into the parts that were originally above, which you can integrate as normal. The part that was originally below the axis, you must take the opposite of it, since that's the definition of absolute value. By doing this, you can find that the total distance traveled is 15, while we found originally that the displacement was 4. Let's now look at a slightly different take on this relationship between position, velocity, and acceleration. In example 4, we again have a particle moving along a line with velocity given by the rational function 1 divided by t plus 1 over the time interval from 0 to 8 hours. This time we know the particle's initial position with respect to the origin, which is -4. That is, at the time t equals 0, it is located 4 units south of the initial place, which is considered home base or the origin. We want to find the position function using the net change theorem, and then we'll find it using the method of antiderivatives. Let's recall what the net change theorem formula is. In this problem, we are looking for a representation for position. We're given velocity. Because we're looking for position, remember that the relationship between position and velocity is that when you have position, its derivative is velocity. This means that we won't need to compute the derivative because we already have it. The velocity is the derivative of position. In this case, then, we need to integrate that derivative over the time interval from 0 to 8. This is using the net change theorem. We'll have the integral from 0 to 8 of the position 1 over t plus 1 dt. To integrate this, we can look at it several different ways. Probably what I would do is I would look at this and think about what I could do to undo the derivative. Now, this is one we have not seen before, so it's not one I would expect you to be able to do on your own now, but after the next couple of days, when you learn the antiderivatives for natural log, you should be able to do it. This is, in fact, the antiderivative for the natural log function. If I were to think about the natural log of t plus 1, and I were to take the derivative of that with respect to time, I would get 1 over t plus 1, since the derivative of the inside function t plus 1 is just 1. This means that an antiderivative to this one is the natural log of t plus 1. We can use that idea to undo this derivative. This will then lead to the following. The natural log of t plus 1, which must be evaluated between 0 and 8. We will also need to consider that whatever goes inside natural log needs to be non-negative. So normally you would get absolute values here. However, because we have t plus 1, and I know the smallest that time can be is 0, I'm guaranteed that t plus 1 is always positive. What would I need to do to complete this particular definite integral? I need to plug in the upper limit of integration, which is 8, and subtract from that the value that I get when I plug in the lower limit of integration, which is 0. In this case, I end up with the natural log of 9 minus the natural log of 1. However, you should remember that the natural log of 1 is, in fact, 0. That means that I can replace the second value here with 0, which tells me that my number turns out to be the natural log of 9. This is simply the center part of the net change theorem formula. Now I need to think about what my initial position was. Initially, I was at location -4. That means to find my new position, which would be f of 8 or s of 8, since we're allowing s to represent position, this would be equal to the position in the initial point in time, 0, plus this integral from 0 to 8 of s prime of t dt. Remember that s prime is velocity, which is why we replaced it there. My initial position is 4 units south of the origin, or -4, and I found that the value of the integral was the natural log of 9. This gives me that particular value for the displacement. If I want to get a generic formula for the displacement, instead of integrating to 8, I could instead integrate to t, as we did previously. If I integrated from 0 to t, then I need to substitute out and use a different variable inside the integrand and differential, since I don't want those to match. I can use anything I want, and this time I think I'll use a star. I know it looks silly, but in fact, this is perfectly acceptable and it does work. This, of course, leads us to reevaluate the natural log of star plus 1 with the values 0 to t plugged inside. We know from what we did previously that the second term will drop out since the natural log of 1 is 0, and this will lead to the displacement function of natural log of t plus 1. Then when we add on the initial condition, our position at some unknown time t could be given by -4 plus the natural log of t plus 1. Now, how could I do the same thing, but instead use the idea of the antiderivative and the indefinite integral? I can solve the same problem in a different manner by using antiderivatives inside the indefinite integral. To accomplish that, remember that I am looking for the position function, which will be the antiderivative of velocity. In this case, I'm looking for the general function, so I do not have limits of integration at all. Remember that my velocity function is 1 over t plus 1 with respect to t. We found previously that an antiderivative was the natural log of t plus 1. However, with the indefinite integral, only gives you the function up to an unknown constant of integration plus c. To find the value of c, I use the initial condition. Since I know that s of 0 was initially -4, then I can complete this by plugging that in. -4 must be equal to s of 0, which must be equal to the natural log of 0 plus 1 plus a constant. However, I know that 0 plus 1 is 1, and the natural log of 1 goes to 0. Because I have that relationship, that tells me that the constant must be -4. This will give me exactly the same formula that I got previously using the Net Change Theorem, which is here as you see above. Let's now look at a different example. In problem 228 from your textbook, it states, a ball is thrown upward with a height of 3 meters at an initial speed of 60 meters per second. We can assume that up is the positive direction, which would make the initial velocity positive 60 meters per second. Acceleration resulting from gravity is negative 9.8 meters per second squared. The negative is because gravity pulls us down, and down is the negative direction in this problem. Neglecting air resistance, solve for the velocity v of t and the height h of t of the ball t seconds after it is thrown and before it returns to the ground. In this case, the height of the ball is actually the position of the ball. Since the ball is being thrown upward, we need to visualize what's happening. Let's draw a general picture just to kind of get an idea. Over here somewhere, I have a tree and I have a person who is tossing a ball in the air. The ball is going straight up, stopping somewhere and falling straight back down. In other words, the ball is traveling along a line. in rectilinear motion. Because of that, we can use the same process we've been using to find our equations. In this case, we'll have to start with acceleration since that's the one we initially know. Let's write down the information, however, that we have. A ball is thrown upward, that's the positive direction, from a height of 3 meters. Okay, that's a really tall person. They must be on a ladder because that's over 9 feet tall. So that means that my initial position at time 0 is 3 meters. The ball goes up in the air with an initial speed of 60 meters per second. That means that when this ball is originally launched, it is traveling at a positive 60 meters per second. The positive is because it is traveling up. Acceleration resulting from gravity is negative 9.8 meters per second squared. This is what we'll use for the gravitational constant. Neglecting air resistance, solve for the velocity v of t and the height h of t of the ball t seconds after it is thrown and before it returns to the ground. So we'll allow our upper limit of integration to be an arbitrary t, and we'll integrate. We need to remember what the relationship is. The derivative of position gives me velocity. The derivative of velocity gives me acceleration, which in our case is gravity. That means that if I do the integral of gravity or acceleration with respect to time, I should get back the velocity function up to a constant. If I then integrate velocity, I'll get back to position. Let's start then with gravity. We need to integrate the negative 9.8 meters per second squared with respect to time, so we use the differential dt. Our units on the limit for the limits of integration are not necessarily clear, but what I need is 0 for the lower limit and some arbitrary t for the upper. That means that I probably want to change out this dt instead and use some other variable that will disappear, like x. This would give me negative 9.8 meters per second squared x evaluated between 0 and t. If I were to plug 0 in place of the variable x, I would get 0. Thus, I only get negative 9.8 meters t per second squared. If we think about it, time will have units of seconds, and 1 second here will cancel one of the 2 seconds in the denominator and leave me with meters per second, which is the unit for velocity. To find the actual velocity at time t, I need to take the net change theorem and add the initial velocity to the result of the integral, which I got negative 9.8 meters per second squared times t. My initial velocity in the problem was given as 60 meters per second. That means that down here, my velocity function must be equal to 60 meters per second plus negative 9.8 meters per second squared times t. That will represent velocity. To find the next one, I will need to compute the position. To find position, I need to integrate velocity. So now I need to integrate velocity. To find position, we'll take the integral of velocity again from 0 to t of 60 meters per second plus, or since I have plus and negative, I could write it instead as minus 9.8 meters per second squared times t. Now, I've got a t already in the limits of integration, so let's again substitute out this dummy variable and replace it with something different. Anything at all will do. For the next step, what I should end up with after I do the integration would be 60 meters per second times t, since it was originally a constant, or rather x. I forgot I changed my differential, minus, for the next part, 9.8 meters per second squared. And to integrate the x, I will get x squared divided by 2. This will need to be evaluated between 0 and t. I can divide the 9.8 by 2, and that will give me 4.9. If I plug in the lower limit of integration, since both terms have an x, it will disappear. Plugging in the upper limit then leads to the following expression for the position function, or height as a function of time. This would be 60 meters per second times t minus 4.9 meters per second squared times t squared. Let's check the units to see if these are really position units. Meters times time would give me meters times seconds. Divided by seconds, this would be meters. In the second one, meters times times squared would give me meters times second squared. Divided by second squared is also going to give me meters. Now, in order to find the true position function, I need to add on to this the original position, which is s of 0. If I add on s of 0 to each of these parts, then I should be able to come up with a formula to give me the position or height of the ball at any time. The initial position was 3 meters up in the air. That means that this is now the formula that I can use to find the position of the ball at any point in time, at least up until it hits the ground again. You may want to consider reordering this equation because it is in fact quadratic. It's just all out of order. The quadratic term is in the middle, the linear term is first, and well, okay, at least the constant term is at the back. You could reorder it, but it's not required. At this point, we want to switch gears and go to something a little bit different. And that is, how do you deal with even and odd functions? When you integrate an even and an odd function, you need to first remember what an even function and an odd function are. An even function is one where if you replace the variable x in the expression with negative x, it does not change the equation. That means that the graph of this is symmetric with respect to the y-axis. Another way of thinking about even functions is that they are, in fact, y-axis symmetric. Let's do an example. There are two examples here of even functions, x squared and the cosine of x. If I were to take x squared and replace the x instead with negative x and then square it, the negative being squared would give me back x squared. In other words, it does not change the function. That means it's even. If you fold on the y-axis, it will fold together and touch. Now let's take a look at an odd function. An odd function is one where if you replace the variable x with negative x, it does not give you the original function, but it gives you the opposite of the original function. These are symmetric about the origin. Both sine and x cubed are odd functions. So is the function 1 over x. Let's look at what happens when I replace the variable x with negative x in the x cubed function. This would give me a negative x times itself 3 times. 3 negatives is still negative, which would give me a negative 1 times x cubed, or negative x cubed. That means I didn't get back the x cubed I started with, but I did get its opposite, so it is odd. If you integrate across a symmetric interval about the origin from negative a to a, then you will get double the area for an even function since you have a symmetric function across the origin, or rather across the y-axis, and you'll get 0 net area for odd functions since they are origin symmetric and have as much above the axis as they have below. This is basically what it would look like in integral notation. Notice that the limits of integration are the same in absolute value, but opposite in sign. Let's do a quick sketch of what x squared looks like so we can understand why we get double the area. If I were to integrate from negative a to a, then I would be getting this area here, which is the same amount of area as that area there, which means that I get double the area from 0 to a. This can simplify the formula for finding the definite integral, since it is the presence of negative values in the limits of integration that cause the most common mistakes. What about for an odd function? The sine function is an odd function. Let's take a look at what sine looks like. If I were to integrate this from negative pi to positive pi for sine, you can see that I have as much area below as I have above. However, because the area below is negative and the area above the axis is positive, these will cancel one another out and give me a net area of 0. This means that when I integrate from negative a to a, I simply get 0. If you don't notice that it is an even or an odd function, you will still get the correct answer as long as you integrate properly. So don't worry too much if you miss this at first. What are some things that might tip you off to think about even and odd? First, notice that the limits of integration both have the absolute value of 2, but they're opposite in sign. Second, notice that the integrand, x to the 4th power, is an even power. That means it's going to be an even function. Let's check it by taking the function f of x equal to x to the 4th and replace the x with negative x. If I raise a negative to an even power, I'm guaranteed to get a positive, which gives me back x to the 4th. That means it's even. Since I'm integrating from negative 2 to 2, that means, like in this picture here, I have the same area from negative 2 to 0 as I have from 0 to 2. That means I can simplify this one by doubling the integral, but only integrating across half the region. This would give me 2 times the integral from 0 to 2 of x to the 4th. The antiderivative for x to the 4th is x to the 5th divided by 5. Now I evaluate between 0 and 2. Notice that instead of having non-zero numbers for both limits of integration, this now gives me 0 for one of my limits of integration. That will greatly simplify the plugging in process. This gives me 2/5 times 2 to the 5th power, since 0 plugged in would give me 0. This results in 2 to the 6th divided by 5, which is the same as 64/5. If you didn't notice that, you should get the same answer as long as you do it correctly. Let's demonstrate that now in a different color so that you can see the process still works. Let's do the integral from negative 2 to 2 of x to the 4th, assuming we don't notice that it happens to be even. If I don't notice that it's even, I'm going to evaluate the antiderivative, x to the 5th divided by 5, and then I will need to plug in the limits of integration from negative 2 to 2. If I plug in the upper limit of integration, this will give me 2 to the 5th divided by 5 minus, and then I will get negative 2 raised to the 5th power divided by 5. Be very careful and use parentheses around the lower limit of integration's value. Otherwise, you're liable to make some careless mistakes with the negatives. Now let's evaluate what that gives us. 2 to the 5th is 32, so that's 32 divided by 5. A negative raised to an odd power is still negative, so this will be negative 32 over 5 inside the parentheses. A double negative is going to make it plus, which would make it 32 fifths plus another 32 fifths, which gives me 64 fifths. Comparing that to what I got the first time, I did get the same value, but you can see that there's a lot more worrying about negatives in here and a lot more opportunity to make a careless mistake. Let's look at one more example. In our last example, we want to integrate from negative pi to pi of the function sine of x with respect to x. Remember what sine looks like. Sine is an odd function. You have this bubble up and this bubble down. We know that this should give us 0. If you remember that sine is odd and you notice that this is a symmetric across the origin interval, then you can go ahead and write equals 0 without showing any work at all. If you forget, however, you can go ahead and integrate and should get the correct answer. To find the antiderivative to sine, think about what you need to take the derivative of to get sine. I would need to take the derivative of a negative cosine of x. Then I will need to plug in the limits of integration from negative pi to pi. Notice that my value for the antiderivative is negative, and I have a negative in the limit of integration, and I will have subtraction between the two limits. This makes a lot of negatives. This will give me negative the cosine of pi minus, open parentheses for the lower limit substitution, of negative cosine of negative pi. Now evaluating these, remember that the cosine of pi is negative 1. This gives me a negative of negative 1. Over here, remember that negative pi means that on the unit circle you went backwards, which is clockwise. That value is also negative 1. However, I have another negative on the outside of that and another on the outside of that. This is going to give me, if I do them in steps, 3 negatives in a row. You can see here why I say that this is somewhat risky and you need to be really careful with the negatives. This will give me a positive 1 for the upper limit of integration substitution, and 3 negatives will give me a minus 1 on the lower limit of integration substitution. 1 minus 1 does give me the same result of 0. Let's look at example 8. In this example, we want to integrate from negative 10 to 10 of the function x divided by the quantity 200 minus x squared. I'm suspicious because negative 10 to 10 is a symmetric interval across the origin 0 on the x-axis. I know that x squared will not change sign even if I replace x with negative x. However, the negative in the numerator means that it will change from positive to negative if I replace x with negative x. That means that this must be, in fact, an odd function. Since this is an odd function, then I know that if I'm going to integrate this, I will get 0 area. Let's take a look at the graph just so you understand why it would be so. Here is the graph of the function between negative 10 and 10. You can see that on the left, it is definitely below the axis. Let's shade in the area on this side with the pink color, which I can barely get in there. And on the right side, let's do it with blue. Can you see that these must represent the same amount of area on the two sides, one below, so it's negative, one above, so it's positive. That means that when I add these together, I will come up with a net area of 0. This is the last example for this video, and this is the end of the video for section 5.4 on various integration formulas and using the net change theorem.